I'm going to talk about estimating a confidence interval for the population using a z-value, a sample average, and a sample standard deviation or variance, whichever way you want to think about it. So let's say there's a population here. We don't know jack about it except for what we have in our sample. Before, when I talked about this, I talked about the population variance, right? I talked about our sample average, and then I also talked about the population average. But we don't know that. We don't know what the average is. We only know our average here, and we know our variance here, or our standard deviation, because we can just take the square root of the variance, right? So what do we do in this situation? Well, I think it tacitly becomes obvious, right? We basically got to use the information we have here. Because we don't know, we can know there's a variance, but we don't even know how the variance would be different. If we don't even know how many are in the population, we don't know the average, we can't compare these against the average in here, we can't do jack, but what we can do. So, what we're going to want to do in this case is pretty much use the average. Oh, let me start with the key. So, x is any individual value. I don't actually use it here, but that's what all these blue things are supposed to represent. And by the way, I made this up, and there would definitely be a way to figure it out, probably. But x with a line over it, that is the sample average. Mu is the population average. So the sample average is what we have here. We don't know what mu is up here. N would be the parent population size. We don't ever use n here. That would be how many are up in this area here. Lowercase n is the number of our sample. How many of these on this histogram did we count or did we look at for a value, right? So I show n here is 300. So this is supposed to be represent 300. It doesn't look like 300 to me, but you get the idea. Sigma squared, that's the variance. So that is how much, if you take every single value here and you subtract it from the average in the middle there, you take and subtract the average from it, then you square it, and you keep adding those together. Even if it's less than or greater than, it doesn't matter. They're still going to get squared and be positive values. We take that whole value, then we take the square root of it, and we get the standard deviation. Now, there's also what's called a z-value, which is a comparison against the average. I put mu here, but in this case, we're going to end up having to use this because we don't know what mu actually is. That's our best estimate, right? So we start presuming, we use a little bit of circular reasoning here. We assume that this actually is mu. We take each individual value, or we take a given individual value, and then we subtract it from the average, and we divide by the standard deviation. We can only use what's in the sample though. So we're going to be a little bit presumptive here, but when we do it, we're going to get a closer estimate than we could have ever had. So, without using a different method at least. So, we know what the sample average is. We know what the sample standard deviation is. Let's say it's 75. I try to kind of guess from what I drew here. And then n, I said 300, but that's not really, that's probably less than 300 there. So if we do that, remember that if you take the variance and you divide it by n, that's a closer approximation to the actual standard error. And that is how much your average is deviating from the population average. But since we only can use our variance from the sample, not the population, and we can only use the n, obviously we use the n from our sample, but we got to take the square root of that, and then we got to decide what level of confidence we want. So if we want an interval of 95%, a 95% confidence level, if this was actually the population variance, we would use 95%. So we're going to use 95% because we don't know what else to use in this case. So we go 1.96 times the square root of this, because this was using the variance, and we want to use the standard error. The standard error is actually the square root of the variance. And this is our variance here, we divide it by n. To get the standard error though, we need to actually take the square root of n, and also we want this in standard deviation form. So when we do that, we end up with 1.96 times the sample standard deviation divided by the sample number, the square root of the sample number. When we do that, we get 1.96 times whatever that was, and we already said that was 75. Take 75 times 1.96, and then you divide that by the square root of 300, and you end up with 8.5. And the average was 260, so we can say that it's basically between 151.5 and 168.5 here. What if we want 99% confidence? You'd have to look at a z table to find this out, but it's 2.58. That's what the z is for that. So you take that z value for 99%, you take it times the square root again of the sample variance, you divide that by n, so that comes out to be 2.58 times the sample standard deviation, and I just gave the standard deviation here, so we can just do the math, we can do the algebra here. Take 2.58 times 75 divided by the square root of 300, we get 260 plus or minus 11.2. So in this case, it would be 248.8 to 271.2. That would be our range. We can be 99% confidence if the actual original population is following a normal distribution. So I hope that helps, and thank you.